Well, we have talked about velocity analysis using the absolute approach, the instantaneous center of zero velocity approach, and using the relative equation, the cross product equation. There's one more analysis that is especially useful, that I find anyway especially useful when we're talking about round things, rolling things, and this is the scalar analysis. All right, so let's imagine here that we have a round object like a ball or a disc. It rolls without slipping. That's a key concept that we'll explore. If it rolls without slipping, there is no relative velocity between the surface and the contact point. There's no relative velocity between the surface and the contact point. If the surface isn't moving, then the contact point isn't moving either. Therefore, the instantaneous speed at the contact point is zero, so it is an IC. All right, so this is a picture out of the book that you can see here, but basically it shows the velocity vectors at different points on a bicycle wheel that's going around the circle. But it shows that at the contact point down here, it's an IC, it's an instantaneous center of zero velocity. It's not moving. So here's just a little illustration with a ruler and a little piece of PVC here. But you can see that if it doesn't slip, then there is no relative velocity between the contact point and the ruler. There would be relative slip if it was being pushed like that, or if it was being torqued and spun like this, then there'd be slip. But when there's no movement, relative movement between the contact point and the ruler, then that is going to be an IC. All right, so let's talk about some math here. We're going to say that the distance on the arc that the hoop displaces is going to be equal to this distance s is equal to r theta, as we know from before. All right, so that's the distance that it rolls on the arc. If it's not slipping relative to the desk or to the flat surface, then that distance s is the same distance that it moves, or that the contact point moves on the surface of the disc. If the contact point is always straight below the center, then that's also the same distance that the center moves. So we're going to say that those three distances s are all the same, and they're all equal to r theta. And if I now take the time derivative of r theta, I can find out the velocity of here. So if s is equal to r theta, I can take the time derivative. S dot is equal to r theta dot, and that's going to be equal to my velocity going in that direction. Well, we recognize r theta dot is r omega. All right, let's take the time derivative again. We're going to say that s is equal to r theta dot. Take the time derivative again. We got s double dot is equal to r theta double dot. Well, we know that s double dot is equal to the acceleration going in that direction, and r theta double dot is going to be equal to r alpha. So we know that the acceleration in this direction is going to be r theta double dot or r alpha. All right, so these relationships apply when there is no slip. All right, so let's talk about relative understanding between what we know and what we don't know. We don't know for sure what all the pieces of this puzzle are, but we know that at this point in time, the velocity of A is equal to 0 if it's rolling without slipping. It's got some omega and some alpha going in this direction, which means it's moving in that direction in a straight line. The center is moving in a straight line with some velocity and some acceleration. All right, so we're going to say that the velocity of O is equal to the velocity of A plus the velocity of O with respect to A. All right, so let's just walk through that. Velocity of O is equal to the velocity of A plus the velocity of O with respect to A, and I should put my little vector widgets on there. So what we're looking for is the velocity of O. In this case, the velocity of A is equal to 0. And what is the velocity of O with respect to A? So the way I interpret this again is if I'm standing on A, what does O look like? If I'm standing on A, what does the velocity of O look like? Well, it's going to be equal to r omega. And whatever that omega is, that's going to be in the I direction. So velocity of O is equal to r omega I, which we've talked about. All right, let's talk about a different point on the circle then. Let's say that it's continuing to go in this direction. We got some omega and some alpha going in this direction. Let's talk about the velocity at point D over here. Well, we can recognize point D as the velocity of D is equal to the velocity of O plus the velocity of D with respect to O. We can find that, we know that the velocity of O is equal to r omega I, which we just solved for. The velocity of D with respect to O, again, is if O was not moving, what would the velocity of D look like? This is a D right there. Well, if O wasn't moving, it would be, if this was a fixed axis rotation, V of D would be going straight up. All right, so that would be R omega in the J direction. So that is now the velocity of D in vector terms, R omega I plus R omega J. And those are the two pieces drawn on the picture there. And so the actual velocity of D is going to be the vector sum. All right, with that I think we have enough tools. We can do a little problem. Okay, so here's a spool being pulled here in this direction. It says that the velocity at the top here is 4 feet per second. So thing to recognize here is at this instant, if the rope is moving at 4 feet per second, the point B is also moving at 4 feet per second. At this instant, they're both going in that direction like that. So we can recognize the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. So I'm going to say that velocity of A is equal to 0, so the velocity of B is going to be equal to this distance times this omega. And we know that distance, the picture here is 3 times omega. I've given the velocity of B is 4, so I can find my omega is equal to 4/3 radians per second. With that information, now I can find out several other things. So I can find out the velocity of D. Velocity of D is the velocity of A plus the velocity of D with respect to A. And the D with respect to A is equal to 2R. So I can say that that is equal to here we are, is 2R omega. I've got an omega going that way, so I can see the velocity of D is going to be equal to 5.33, and it's in the I direction as well. Velocity of O is going to be 1R omega, 2.667. How about the velocity of E over here? Well, we could look at the relative scalar analysis from several points, but it's probably easier to look at the velocity of E with respect to O. So let's say that velocity of E is equal to the velocity of O plus the velocity of E with respect to O. We've already solved for the velocity of O is equal to R omega I. Now, what is the velocity of E with respect to O? If I'm standing on O, what does the velocity of E look like? Well, we know that there's an R. It's going in this direction. It's going to have an R omega term in that direction. So this is going to be minus R omega in the J direction. It's got a velocity of O of positive R omega in the I direction. And those two components put together through the vector sum is the actual velocity of E. Okay, let's do one more here. This one, what we're going to suggest here is that it's not resting on a surface that's still. This one is resting on a surface that's moving. All right, so we got the spool, same spool. It's getting pulled in this direction, and we're given the velocity of B, which is equal to the same velocity as the rope out here. But we're going to say that it's not slipping. A is not slipping relative to this cart or this whatever this thing is. It's a thing on rollers here. So the cart is being pulled in this direction at 2 feet per second. So that means the velocity of A is also going in that direction at 2 feet per second because it's not slipping relative to that. To find the velocity of B, we just set up the relative equation. Velocity of B, velocity of A, velocity of B with respect to A. We've got the velocity of A is given here, and that's going to be negative 2 in the I direction. So that would be equal to negative 2I. Well, I guess I'm given also the velocity of B. Velocity of B is going to be positive 4 in the I direction. All right, and the B with respect to A, again, is if A was not moving, what would B look like? Well, it would have this distance times this omega. There's going to be an omega going in this direction. So it would be, this distance is 3 times omega, and I can solve for omega as 2 radians per second. What is the velocity of O now? Again, the velocity of O can only go in this line right here. So we know the velocity of O has some value going in this direction, but we can set up the relative equation. We can say velocity of O, velocity of B, which I've given is 4, minus plus the velocity of O with respect to B. Now here we're kind of upside down, but we're going to say that if I'm standing on B, where does O look like? Well, if omega is going in this direction, this would be the relative term. It would be negative this distance times omega in the I direction. So it would be minus 1 omega I, and that would be equal to 4 minus 1 times 2 omega, and that would be 2 feet per second. So the velocity of O is still going in this direction, but it has this negative component of the O with respect to B. Okay, let's try another little situation here. Okay, so here, what I want to do is contrast round rolling things with fixed axis rotation for some additional insight. But if we consider this round rolling thing rotating about A is an instantaneous center, it behaves identically to a fixed axis rotation of like a bar with a pin connection here. So I'm going to put a big equivalent sign right there and say that the velocity of O, which is basically rotating about A, and with some omega, is equal to r omega. That's the velocity of O. Same thing here. Whatever this point here, we'll call it O. If whatever that distance is going to be tangent to the curved path with some omega, it's going to be velocity of O. So basically, A is the instantaneous center in both cases. All right, and the same thing would happen, or a similar kind of thing would happen if we had fixed axis rotation instead of rolling without slipping. But if we had a B going in this direction, we'd have a C going down in this direction if it's moving in this direction. If I put it on a bar, I'd have a velocity of B going this direction. If the bar moves to the other side, then I have a velocity of C going down, again with that whatever that R is times omega. So there's a velocity profile here that we would recognize about the IC, and we're going to say that all of those points are going to be related through their distance. They're all going to have the same omega, and they're all, but the distance would be varying so that there would be differing velocities depending on which point because they have different radii. Okay, let's try this round rolling thing. Same thing here. If I know that the velocity of the B at the top is equal to related to the omega, and I've got two r's here. Let's say that we got an r to the very top and another r to the bottom, so I got 2r omega. Same thing over here. Got the velocity profile again. And so what we can look at is we can put a family of curves here that as long as we're connecting perpendicular lines from the velocity vectors to the point of rotation, we can say that the velocity varies uniformly from the point of rotation. Same thing here. We can find the velocity at any point along this vertical line, or along this line perpendicular to the point of rotation. Okay, now what about this guy? This one has a point of rotation in the middle of the bar, but the same kind of concept applies, where there's a family of not really curves, family of velocity profiles that would apply and going in both directions about the instantaneous center. We know that omega is equal to omega everywhere on a rigid body, so that kind of velocity analysis applies. Okay, so here's another one. Here again we're connecting perpendicular lines to velocity vectors, and we can, if we're given one velocity, we can often find more velocities. And then, so in this particular case, we're going to say we're given velocity of A, and we're given the velocity of B. We may want to find out the velocity of C. Well, again, the velocity profile still applies, and what we're doing here is we're drawing the velocity vectors in a relative, the length of which are relative to their, or are related to their magnitude. So if we make those lengths relative to their magnitude, then we can again see that there's a family of velocity vectors that apply here. And all we have to do is find out some distances, and we can find out what our VC is of r omega. Now the next thing that's really cool is we can find out where the instantaneous center is. What we can do here is we connect a perpendicular line to all those velocity vectors, and a line connecting the velocity profiles, and we can find out that the instantaneous center is right down there. In this case, everything is rotating at this instant about the instantaneous center. Even though it has some translation, if I just look at just this piece, you think, oh, it's translating. But at this point in time, what it is, it's rotating about there, and so it looks like it's got translation, but it's actually all just rotation about the IC. All right, so here's some insight that I want you to just kind of follow. Our general case of instantaneous center says that if we know the velocity of B and we know the velocity of A, we can find an instantaneous center of zero velocity. If the velocity vectors are parallel like this, I try to connect the perpendicular lines, but I see that if the velocity vectors are the same, it's just moving in one direction. It's just moving in one direction. So omega is equal to 0 if those two velocity vectors are the same. The same thing would apply whether the bar is straight like this or whether the bar has a slant. And we can see that if those velocity vectors are the same, if they're the same magnitude, the bar is just moving, translating in that direction. So if VA is equal to VB in this kind of picture, omega is equal to 0. The other way we can know that omega is equal to 0 is when we try to connect the velocity, or try to connect the perpendicular lines and look for the instantaneous center. We see that the lines are parallel. We also know that they are that the bar is not rotating through that kind of analysis. Okay. Let's just keep extending this just a little bit. Now let's say that the velocity of A is a little bit smaller than the velocity of B. They're still going in a straight line, still going this way, and I try to find out the omega. This is what I'm looking for, is the omega. So I try to connect the perpendicular lines to find the instantaneous center, and I can see that they're still parallel. If they're parallel, then that means there is no instantaneous center. If there's no instantaneous center, there's no omega. So what it says is that if the velocity vectors are not the same magnitude, there's no omega, which means that, but they have to be, but it has to have an omega if the velocity vectors are different. So it basically says that this kind of condition does not exist. If you see this in a problem, that would be a trick, and it doesn't exist. If the bar is rigid, anyway. If the only way for this to work was if the bar was a rubber band or something like that, and it was actually, you know, decompressing as it's going this way and getting shorter or something like that. All right, so the only way for this kind of condition to exist at all is if VB isn't acting alone. In other words, if there's a VBX, it has to have a VBY. And if the VBY is part of this total velocity of VB, then we can say that yes, it has a VBX that may be bigger than VAX. It also has a VBY, and now we can find, once we find the vector sum of that, we can connect the perpendicular lines to the actual velocity of B and the actual velocity of A, and we can find that there's an instantaneous center down there. So the takeaway from this is, if you see velocity vectors that are the same, that are parallel, the velocity vectors that are parallel, that means that there is no instantaneous center and the bar is not rotating. So again, this condition does not exist. So look for problems like this, where in this case, we know that if this wheel is going in this direction, we know the velocity of A has to be going in this direction. If the velocity of B is constrained to move along this rod, and that is going in that direction. So if those two velocity vectors are parallel, we don't even have to know the magnitudes. If those two velocity vectors are parallel, we try to connect the perpendicular lines, and we see that omega is equal to 0 at this instant. Okay.